Welcome to this class on Neuroscience of Human Movement. In this class, we will be talking about action potential. So, this is part 4 of our discussion on action potential. So, in this class, we will be talking about an important property of action potential, which is propagation. So, whenever something moves from one point to another, you call that it has been displaced, it has moved. So, this is propagation of information. That is one. So, whenever you say that something is getting displaced, the second question that arises is how fast has it been displaced? That is related to conduction velocity in this case, and what are the factors that affect conduction velocity. So, these are the three topics we will discuss in today's class: propagation, velocity, and factors affecting conduction velocity. Right. So, at rest the axon or the neuronal cell membrane is at resting membrane potential, right. So, that means the inside of the cell is more negative when compared with the outside, and at some points either due to a stimulus or due to the opening of voltage gated sodium channels, for a brief amount of time the membrane will become more positive. This situation is called as action potential, and action potentials are usually initiated near the cell body or the soma. We will discuss that in the next slide. So, whenever the initial segment of the axon fires an action potential, then this potential has the tendency, has the ability to cause action potential in neighboring regions, because it turns out that the amount of sodium that enters through the voltage gated sodium channel propagates or basically diffuses through the intracellular fluid. So, causing the nearby areas to become depolarized, and this depolarization, when it crosses the threshold, will cause the neighboring voltage gated sodium channels to open. So, this is the mechanism which we will also detail in the next slide. So, the neighboring area becomes positive, and then the nearby area, the previous area remains inactive. Okay. So, at the active site, positive charges, basically sodium ions, flow to the adjacent inactive area. This local current flow or diffusion causes the adjacent site to be depolarized to threshold and fire action potentials in that region. So, at each point on the membrane, a new action potential is generated. But the original region will repolarize back to resting membrane potential. How does this happen? Let us discuss this in a bit more detail. Right. So, here is a neuron and its input and output structures with some detail. Right. So, here are dendrites, which are major input structures to the neuron, and here is the axon. This is the axon, which is long cable like output structure of the neuron, and this terminates in the axonal terminals or axon terminals. Right. So, these are called axon terminals. They communicate with, say, other neurons or maybe muscle fibers, etc. Now, the neuron has a cell body, which is this, and a nucleus. Right. The neuronal cell body is called as soma. Okay. The point where the soma attaches to the axon, the neighborhood is called as axon hillock. Okay. This is the region where there is a relatively high probability of action potentials getting generated. Okay. Now, these dendrites receive inputs from multiple sources. They may be the same neurons, or they may receive input from multiple neurons. For our purpose, we will discuss how the input enters and causes an action potential in this neuron, without going into the details of how the previous neuron causes an action potential in this neuron. For now, let us suppose that this dendrite is receiving enough information or stimulation that causes a relatively small depolarizing current or a relatively small depolarization. Say, for example, this small depolarization is probably not enough to cause an action potential in this neuron. Suppose it is possible that the same dendrite receives multiple stimulations one after the other closely followed in time. So, before the previous stimulation or before the effect of the previous stimulation dies down, the next stimulation comes in. This leads to a situation where if the response is like this, then the next input will cause a response like that, and the next input will cause a response like that, and the next input will cause a response like that. This case, the output, the response is summed over time. This situation is called as temporal summation. Okay. We will also discuss this in some detail in future slides. What is also possible is the dendrites from multiple sources, say from multiple regions, can receive inputs at the same time. So, at a given point in time, multiple inputs arrive from various different dendrites that are spatially distributed. They all arrive at the cell body at approximately the same time. This will lead to a situation where all these responses from these multiple inputs can sum at a given point in time. This kind of a situation is called as a spatial summation. Okay. Without referring to how an action potential is generated, whether by spatial summation or by temporal summation, we will look at how action potential gets propagated. That is of interest for us in this class, right. Let us assume that an action potential is generated either by spatial summation or by temporal summation at this point. Now, it has to be communicated, it has to reach, say, that point, right. How does it travel from that point to that point? How does it travel? That is the question. Now, let us take a deeper look. Let us assume that an action potential is generated at that point, right. So, essentially before the action potential came in, before the action potential arrived or before the action potential was generated, this part of the axon was at resting membrane potential. And what is the resting membrane potential? It is about minus 65 millivolts, say for example. So, or in other words, the inside of the axon is negative when compared with the outside. The inside of the axon has more negativity when compared with the outside. So, that is the usual case, right, and making it less negative is what is called as depolarization, right. This we discussed in previous class. An action potential causes a transient brief depolarization sufficient to take the inside of the membrane more positive, right. This is what we saw in the previous class. An action potential essentially makes a very small region of the membrane, like that region. So, when we zoom out is that, right. So, that is this region alone zoomed out. In that region, a relatively smaller area becomes positive here, see for example like this, okay. When compared with the outside, the inside is more positive. Let us remember that this is a transient event. This is going to go back to inside negative very soon. Why? Because of the restorative mechanisms that we have discussed earlier, and also because the sodium conductance does not remain high for a long period. It remains high for a very brief period and then becomes 0 or very small value, and then the potassium conductance increases and remains high for a relatively long period. This is what we saw. Because of this reason, this is a transient phenomenon. For a brief amount of time, the inside of the cell becomes more positive than the outside, but that amount of time is sufficient to let in a lot of sodium inside. This is the behavior of the voltage gated sodium channel that we saw. A lot of sodium enters inside, taking the inside of the cell to a more positive value for a brief amount of time, and that sodium when it enters actually diffuses in both directions. And if the amount of sodium that enters is sufficient to take this voltage gated sodium channel to threshold, which it does usually. So, this voltage gated sodium channel goes to threshold, and once it crosses threshold, what happens? Basically the activation gate of this voltage gated sodium channel opens, and the inactivation gate is trying to close. In the meanwhile, a lot of sodium will enter through this gate, not through this gate. At that time, at around the same time, this gate will be, its inactivation gate will be closed, or it will be inactivated, or it will be in its refractory period, which we saw in the previous class. So, a lot of sodium enters inside, and in this channel a lot of or I am going to call this as channel 2. In channel 2 a lot of sodium enters inside, and the sodium diffuses in both directions. Depolarization from this voltage gated sodium channel takes the neighboring voltage gated sodium channel to threshold, and the depolarization of that takes the neighboring voltage gated sodium channel to threshold. Depolarization of that will take the neighboring voltage gated sodium channel to threshold. So, essentially you will have action potential first here, and then another action potential here, and then another action potential there, another action potential there, another action potential there, another action potential there. Note, at each point a new action potential is generated, right, because of the voltage gated sodium channel at that point. Now, the question is, why sodium entering from this region is not sufficient to cause an action potential in, say, this region. So, let us assume the location of these channels are such that, or the distribution of these channels along the membrane are such that the sodium entering through channel 5, when by the time it diffuses, the strength or the amount of sodium that reaches channel 3 and channel 2 are not sufficient to take channel 3 and channel 2 to threshold, but channel 4 can be taken to threshold, but it is in its refractory period. Then the only channel that will get depolarized due to the sodium entering is the channel in that direction, which is basically channel 6, that will go to depolarization, and so on and so forth, which is why action potential is usually unidirectional. It usually travels from that point to that point in that direction, right. So, this is how action potential travels from one point to another. Essentially, it is not action potential that is traveling, it is sodium that is traveling from one point to another. At each voltage gated sodium channel, you have a new action potential that is getting generated. Then the next point is about how fast can this travel. The speed at which action potentials are conducted is called as conduction velocity, and there are two factors that govern the conduction velocity. One is the time constant tau, the other is the length constant lambda. Now, let us remember that the cell membrane can be considered to be a parallel plate capacitor. Okay. So, there is some distance d, and this parallel plate capacitor has, say, some membrane capacitance Cm. And also remember, the movement of ions through the channels are also governed by the channels opening or closure. If the channels are closed, then the membrane has high resistance to the movement of that ion, or if the channel is open, then the membrane has relatively low resistance. We saw these things earlier. We said that there is quantity conductance which varies as a function of time, and depending on the conductance value, the contribution of each ion to the membrane potential will vary, is something that we saw earlier, is it not? So, that means the membrane also has some resistance Rm. So, it turns out that the time constant is Rm Cm, similar to what we would find in basic electrical engineering, right. The time constant is Rc. Here we find that the time constant is basically the product of the membrane resistance and the membrane capacitance. Okay. So, what will take the time constant to a high or low value is something of interest for us, right. So, when the membrane resistance is high, then basically current does not readily flow through the membrane, right, which makes it difficult to change the membrane potential. Thus, increasing the time constant. So, when Rm is high, basically time constant is high. When Cm is high, what happens is that the injected current must essentially first discharge the membrane capacitor before it can depolarize the membrane. So, essentially when Cm is high, then tau is high. So, both Cm and Rm, when they increase tau due to these physical reasons, right. What about the length constant? Essentially length constant is proportional. So, length constant is proportional to the square root of Rm and Ra. To what extent the depolarizing current will go along a neuron before it loses the strength is the question, right. This will if I were to design the system, this will give me an idea where do I place the next voltage gated sodium channel. You do not want them to be placed too close or too far away. If the voltage gated sodium channel is spread, for example, too far away, it is possible that the sodium current will not be sufficient to cause the action potential in that one. So, to what extent can you travel? That is the question, that is given by the length constant lambda, right. And I said lambda is basically square root of Rm divided by Ri, okay. So, where Ri is the internal resistance, and we know something from metallic conductors, right, and their resistance is basically R is rho L by A. Basically as the length increases, the resistance increases, and as the area increases, the resistance decreases. A similar situation is true also in the biological membrane. The internal resistance is low when the diameter of the neuron is large, right. So, one way for me to have a relatively large length constant, one way for me to ensure that the depolarizing current will travel the far distance is to ensure that the nerve diameter is relatively large. The larger the diameter, the lower is the resistance Ri, and the larger is the length constant. To increase the length constant, I can increase the diameter and thereby reducing the internal resistance, but I cannot keep on doing this. If I keep on doing this, at some point body size related constraints will come into the picture. As I said, the internal resistance is inversely proportional to the cross sectional area, therefore larger the fiber, basically the internal resistance will be lower, thus increasing lambda. The other way is to use an efficient method, which is myelination. Myelination is basically an insulator of the neuron or the neuronal axons that increases the membrane resistance. So, that means what? Lambda, if it is proportional to Rm by Ri, if I insulate the neuronal axon with insulator is to increase the nerve diameter. The other way of increasing lambda is to increase Rm simply. That is possible by using an insulation around the neuronal axons, right. So, basically myelination increases membrane resistance and thus increases lambda. But what myelination also does is that it decreases membrane capacitance. So, here what you have is myelination. So, this is myelin, these are basically neurons or glial cells. These are glial cells that insulate other neurons, basically that insulate, and this insulation happens in multiple layers, right. Between two patches of this insulation there is a gap, between two of these insulations there is a gap, and that is called as, this gap is called as a node of Ranvier. What happens in this node of Ranvier? Suppose I have this node of Ranvier and I am zooming out this. What is actually happening is that there is a great increase in the density of voltage gated sodium channels and voltage gated potassium channels. So, the density of voltage gated sodium and potassium channels is very high when compared with the rest of the axon which is passing inside the insulation. So, this leads to a situation where the action potential can be quickly generated here. Why? Because membrane capacitance is reduced. Essentially, let us remember, tau is RMCM. When Cm is reduced greatly, right, this will lead to a situation where tau is reduced to a large extent. This means by myelination I can increase the length constant and I can decrease the time constant. So, multiple factors come into the picture, some of these are not discussed. It is sufficient to know that the distribution of the voltage gated sodium channels and the voltage gated potassium channels is high at the node of Ranvier, so that action potentials are quickly caused in the node of Ranvier when compared with other regions. So, and sodium cannot escape through the membrane because there is insulation. So, once sodium enters here, it diffuses and causes action potential at this point, and once sodium enters here, it diffuses and causes an action potential at this point. So, when we are looking, say there is a person here, there is a person here, let us assume that is a person, this person is watching, an action potential is generated at that point, and after a very small gap in time an action potential is generated at that point, and then an action potential at that point, and an action potential at that point, an action potential at that point, and then an action potential is generated at that point. It seems as if a wave of action potential is arriving towards this person who is observing from this point, right. For this person, a wave of action potential seems to be arriving, and it seems as if the action potential is jumping from this point to that 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 point, right. It seems as if the action potential is jumping. Actually it is not the action potential that is jumping, right. So, this situation where an appearance of conduction as if it is jumping is called as saltatory conduction. Okay. This is called as saltatory conduction. Salt or saltatory has its roots in dance, as in dance, jumping conduction. So, in summary, what we have seen is action potential is conducted through saltatory conduction in myelinated axons, and the conduction velocity basically depends on time constant and length constant, and the time constant can be reduced by myelination. By essentially myelination reduces time constant, and the length constant is increased by increasing nerve diameter, but there are limitations as to how much you can increase the nerve diameter using this. Okay. So, with this we come to the end of this lecture. We will continue this discussion in future class. Thank you.